Next, let's study the two most important theories at the very beginning when people try to build the quantum physics. So the first one is the de Broglie hypothesis. So what the de Broglie proposed in the 1923 is that, so from the photoelectric experiment, originally it is a light, it is a wave, but they carry the wave properties, so we can define the momentum and the mass. And the particle property of the wave is a photon, it is a particle. So de Broglie say that if this is true, then I can claim that if originally it is a particle moving in the space, do they carry the wave behavior as well? So the answer is yes. And this is a very important step to understand the quantum physics, is that no matter you thought it is a wave or it is a particle originally, intrinsically, they carry both the particle and the wave behavior. So based on that, the de Broglie proposed that the same relation we just used to describe the photon can be used. And what he did is just sounds like pretty trivial to you now, but what he says is that now if it is a particles, then the wavelength carried by this particle is h divided by p. P is the momentum carried by the particles. So for the people who cannot distinguish the difference, then let me go back to the slide. Here it is a light with a wavelength lambda, and we try to quantize them. So you know the wavelength of the light. So now after the quantization, the particle carry the momentum p. It is described by the h divided by lambda. So which means we know lambda first for the wave, and we go to the particle. But based on what de Broglie proposed is that now it is a particle, so you know the momentum. And based on the momentum carried by the particle, you can find out what is the wavelength of that particles. So this sounds, actually, it is just saying the same thing in the reverse way. But if you try to go back to the time around the beginning of 20th centuries, people actually never think that there's a so-called duality issues. They always thought wave is a wave, particle is a particles. So the thesis actually written by the de Broglie, I agree that it is more philosophical argument, that this one is more conceptual, not related to mathematically. So you can see how trivial the math it is. But de Broglie won the Nobel Prize based on this thesis. So you can see that how important it is. So I'm going to provide you more information about the de Broglie hypothesis. But now let's go through the first conceptual quiz today. So this one will be the first unanswered conceptual quiz. But before I jump to the next slide, I want to give you some hint. So now electrons are the proton of the particles. So they are moving and they also have their own mass. So how did you find out the wavelengths produced by the electron and proton using the concept of the de Broglie hypothesis? Is the way to answer this one. Now, let's go back to one of the experiments I introduced you in the chapter 28, the double slit experiment. What people find out is that when you provide a light source here, and when the light passing through the double slit the instrument here, they find out they will produce a periodical pattern here, which you have the bright, dark, bright, dark, bright patterns repeated here. And apparently, the only way to understand this kind of interference is the wave properties. So this is the reason when we mention this one, people say, okay, now we should probably try to treat the light as a wave. However, if the de Broglie hypothesis is correct, then if it is not a wave, not a photon, if it is a particle, for example, electrons, so we always thought the electron is a particle, yeah? So when the electron source is provided and passing through the double slit instrument, do they also produce this kind of interference patterns with a constructive this destructive pattern repeatedly. And the answer from the instrument, from the lab is, the answer is yes. So if you provide the electron beams, obviously you cannot see it in terms of the bright and dark section, but you will see that the distribution of the particles. So you will have more electron here and almost no particle here and more electron here. So this one actually is a very important evidence for the de Broglie hypothesis. So what happens is that the particles also carry the wave properties. So when they're passing through the double slit, the electrons will behave like a wave instead of the particles. But here I have to explain one thing, is that how wide the slit is very important. If you try to provide the electron as a source, then you should try to narrow the width of the slit to the size of the electrons. Okay, so if you make the size of the slits is much bigger than the electrons, for sure you are not going to see this kind of interference patterns. This is something I have to emphasize. You always have to choose the size of the slits is close to the size of the electrons or the particles. So if they are close, then you will see that the wave property will become important, and they will start to have an interference pattern built due to the constructive and destructive interference. However, originally, if you try to think that the electrons is a particles, you will saw that, okay, classically, when the electron is shooting to this direction, I can predict exactly where the electron is going to land. For example, the electron is going to land here, it is going to land here. So ideally, if you provide enough information of the initial velocity, which including the magnitude and directions, ideally, you should be able to tell where the electron will land. But what people find out is that, no, we cannot predict any particular particle where they are going to land. So when the pattern builds, we can only see that or predict the so-called final patterns. And let me show you a photo, then you will know what happens. So if you shoot electron beams, then originally you will see that it is like a random distributions. The electron will land here and there, so you cannot find out the patterns. There's no way you can predict that. But when you shoot more and more electron beams, eventually you will see these patterns. And this is the patterns you can predict. But at the very beginning, for the individual electrons, there's no way you can predict where it is going to locate. So this double slit experiment for an electron as a source also proved that the de Broglie hypothesis is correct. Because if the particle is a wave, ideally, you should be able to find out they are going to land at the particular regions. But in fact, no, it behaves like a wave. So this is the concept. The particle carry the wave property. So I will say that it sounds trivial, but I will say it is also not that easy to understand. So, but let's follow the conclusion we just have, is that if the particles carry the wave properties, then we are going to study the second important concept in theory, which is the so-called Heisenberg uncertainty principles. So I just mentioned to you is that we cannot predict exactly where the electron is going to land. So there's an uncertainty there. We can only predict the final pattern there. So it is impossible to describe the motion of the individual particles precisely. But this is actually contradict to the classical physics. In classical physics, we believe that the motion of the particles can be described 100% precise and correctly if you provide enough information. But this is not true. When you try to treat the particle like the electrons or the photons, they are very tiny particles. So in that case, something different happens at that small scale. And this is the beginning of the quantum physics. So intrinsically, this uncertainty happens is due to the wave properties of the particles. So if the particle do not carry the wave property, there's no way this kind of uncertainty will happen. So remember now that the key sentence here is we cannot describe the motions, the position of the electron precisely for individual one. We can only describe the distribution of a lot of electrons as a pattern. So, for example, in this case, we have the interference, and let's focus on one of the slit, and the width of the slit is capital W. So the angle for the first dark fringe is theta, and this is the central fringe. So you can calculate how wide the first central fringe it is. So if you use this trigonometry relation now, you can calculate that the width, how wide the central maxima it is this. So the angle theta can be related to the wavelength of the particles and the width of the central the slit. So originally, if you follow these equations, then you will say that if you make the slit narrow and narrower, if you try to make the central peak narrower, you can try to make the wavelength shorter and shorter. So if this is smaller and smaller, then this one will become smaller and smaller, yeah? Because theta should be the same. So what you're doing is that you try to make it narrower. But this one actually is not correct. Because based on the de Broglie relation, when the wavelength becomes smaller and smaller, the momentum will goes up. So what does that mean? If you try to determine the position of the electron more narrower, more precisely, then you will lose some information, which means the momentum carried by the momentum carried by the photon will be bigger, which means the deviation carried by the electron, the momentum, is bigger and bigger. So which means that if you try to make the distance more precise, you will lose the information in the momentum, which the uncertainty is always there. No matter the uncertainty is in terms of the position or in terms of momentum. So this is the first format of the Heisenberg uncertainty principles. So here I say that if the position is described more precisely, then the momentum is more uncertain. And vice versa. If you try to make the momentum of particle more precise, then you have trouble to describe the position. So the position is less precise. I'm not sure that this is a clear concept to you. So let's go back to this slide. So use the interference pattern here is that you can consider the interference pattern is how the electron distributed. Yeah? So if more and more electron distributed at the center here, which means the position of the electron is more precise. You can describe them precisely. However, in that case, the momentum of electrons is imprecise. However, now if you have a broader range of the central maxima here, so the electron could be here, could be here, could be here. In that case, the position is not precise, but which means that the momentum carried by the individual electrons can be described precisely. This is the Heisenberg uncertainty principle, and this is an intrinsic property in the quantum physics.